Most PKI outages don't come from broken crypto. They come from misunderstood requirements. In this module, you'll learn how to turn messy business, IAM, and compliance needs into a clear, prioritized PKI use case portfolio that actually drives your architecture and design. Before you touch crypto settings or stand up CAs, you need a map of where trust really shows up in the organization. Think in terms of use case clusters. Today, you might only see AD certificates, a legacy VPN, and internal Wi-Fi. The future almost always adds standard TLS everywhere, IoT provisioning, zero trust device identity, mTLS for microservices, and DevOps pipeline signing. Your role as a PKI engineer is to design one coherent trust fabric that can support all of these over time. Every PKI use case lives somewhere on an impact versus scale quadrant. High impact, low scale includes things like PAM access or offline routes. Very few certificates, but if one breaks or is compromised, the blast radius is massive. High impact, high scale covers public-facing TLS or zero trust device identity, where both security and reliability must be extremely high. Lower impact quadrants still matter, but there you optimize for operational efficiency and automation, rather than the strictest possible controls. You can think of your PKI as a bridge. Today, the current base is generally strong enough. RSA 3072 or 4096, SHE 256 or 384, ECDAs for key exchange. But parts of that bridge are already moving into the deprecation zone. RSA 2048, older hashes, and legacy key exchanges. Your job is to design a path from this base to a future state with post-quantum and hybrid schemes, so algorithms can be swapped through policy, not through emergency rebuilds. When a certificate is revoked, there are three main ways to signal that to the world. SARLs are the classic batch mode option, high latency, but very reliable and easy to audit. OXP brings low latency per connection checks at the cost of more infrastructure load. OXP stapling prefetches and caches those responses, offloading the responder and improving performance. Your compliance targets, like NIST 800-570 Web Trust, will heavily influence which combination you standardize on. Identity-centric PKI only works when three engines turn together. Directories and identity providers assert who the subject is. PKI binds that identity to a key pair and issues a certificate that can be validated anywhere. Zero trust policy engines then consume those certificates as high-confidence signals for access, posture, and step-up authentication. If any engine is misaligned, directory data, certificate design, or policy logic, the whole security model slips, even if each component looks healthy in isolation. For the highest privileges, design PKI around two parallel flows, humans and services. For administrators, certificates act as the keys to a privileged bastion. You authenticate with a strong certificate, then pivot to target systems from that hardened island, not directly from your workstation. For services, your internal security token service signs SAML or OIDC tokens and uses mutual TLS between APIs, extending zero trust controls safely out to cloud workloads. Designing PKI also means deciding how trust crosses three main zones: deep on-prem, the DMZ or management networks, and the cloud edge. Each boundary introduces friction, firewalls, latency, and air-gapped or partially disconnected segments. The same controls that protect your CAs can break auto-enrollment, OCSP, or API-driven issuance if you ignore them. Your goal is to map these constraints explicitly, then decide where you'll tolerate delay, where you'll cache, and where you need paths to stay real-time. 99.9% availability isn't about a single magic product. It's about removing single points of failure across the whole PKI path. You cluster issuing CAs and back them with an HSM cluster, so key material survives node loss. You geo-distribute OCSP and CRL endpoints so revocation checking continues to work. And you treat disaster recovery as engineering, not paperwork. Key escrow, tested CA recovery, and regular failover exercises that prove the design actually works. This matrix is how you turn messy requirements into concrete PKI design decisions. Each use case gets a default algorithm, a revocation expectation, an IAM integration, and an availability target. Public web, TLS leans on familiar RSA and standard CRL or OCSP. Internal device trust moves toward ECC, and tighter integration with MDM. PAM admin authentication pushes both crypto strength and availability hardest, driving HSM use and immediate revocation. Ephemeral IoT flips the model. Very modern algorithms, almost no revocation, and aggressively short lifetimes. You can also view PKI as concentric trust zones. At the center is the offline root CA and HSM, air-gapped, rarely touched, and protected with the strongest physical and procedural controls. Issuing CAs sit one step out online, but tightly locked down and reachable only from admin networks. Registration authorities handle enrollment workflows and identity proofing. Farthest out is the consumption plane, where clients and applications live. As you move inward, security controls must increase dramatically. In a mature PKI, controls are never sprinkled randomly. You start from clearly documented threats, then attach specific architectural mitigations. If you're worried about root key compromise, you respond with strong key custody, FIPs grade HSMs, offline roots, and tightly scripted ceremonies. If the risk is unauthorized high privilege issuance, you use dual control RA processes and IAM guardrails. And if endpoint misconfiguration is the problem, you lean on CLM automation to enforce consistent policy at scale. This blueprint shows how abstract requirements become a concrete CA hierarchy. At the top, an offline root anchors trust and changes very rarely. Beneath it, policy CAs represent major trust domains, such as workforce versus devices, often driven by regulatory or lifecycle differences. Each policy CA then delegates to issuing CAs tuned to specific risk: privileged access, standard users, mobile or MDM, and IoT. You design these tiers around isolation, blast radius, and how independently each domain needs to evolve. A policy-driven certificate is really three stacked layers of decisions. At the bottom is the cryptographic layer: which algorithm, key size, and validity period you allow. That's your risk versus performance trade-off. Above that sits the policy layer: key usage, EKUs, and constraints that define what this key is allowed to do. On top is the identity layer: subject and SAN design that ties the certificate cleanly into IAM, directories, and access policies. Traceability is what turns a pile of PKI decisions into an auditable, defensible design. Start from the use case, like high-risk admin access. That leads to a security requirement, such as phishing-resistant identity. Then capture constraints, for example, needing smart card or FIDO integration. You select risk mitigations like dual control and hardware key storage. Finally, you define concrete design outputs. In a well-run PKI, nothing exists without a clear upstream requirement.